Let us continue our discussion of the subject computer organization. And last time we had seen the basic concepts of pipelining, then data hazards. In this session, we will introduce instruction hazards. Pipelining, the purpose of pipelining we remember is for performance improvement, while the delays or the stalls in pipelining will cause hazards, and hazards can be data hazards or hazards can be instruction hazards. So let us look at instruction hazards today. So as you can see, as mentioned here, a pipeline stall is a pipeline delay. Okay, so this pipeline stall or pipeline delay is caused whenever an instruction fetch unit is interrupted. What is the job of an interrupt instruction fetch unit? It will be fetching the steady stream of instructions. So let us look at this diagram and let us try to check what is happening here. Okay. So you remember a term called as cache ratio, cache hit ratio, cache hit, cache miss. So if the instruction being search is available in the cache, then it is a hit. If it is not available in the cache, then it has to be brought from the main memory, then it is a miss. So here this diagram, figure 8.4 from Hamashar textbook, depicts cache miss in F2. So as you can see here, we have instruction 1, instruction 2 and instruction 3, and every instruction has these four stages: fetch the instruction, decode the instruction, execute the instruction and write the instruction. At instruction 2, fetch 2 is stalled. Fetch 2 is delay. As you can see, it is taking more number of clock cycles. So as it is taking more number of clock cycles, as it is delayed, as it is stalled, so this is stalled or delayed because of a cache miss at fetch 2. And you can see the effect of that. The effect of that will be the decode one also will be idle, the execute one also will be idle for 3 clock cycles, and write one also will be idle for 3 clock cycles. Pipeline stall, as you can see, was caused because of cache miss, but pipeline stall can also cause because of branch instructions too. And instructions are either conditional branch instructions or unconditional branch instructions. So let us look at the unconditional branch instruction pipeline stall. Okay, so pipeline stalling is delay, and with this delay, the time is lost, and this loss is caused because of branch instruction, which is an unconditional branch instruction, and this is called as a branch penalty. This is called as a branch penalty. Now, what should be the job? The job should be to reduce this branch penalty. Okay. So, how do I reduce the branch penalty? You need to compute the branch address earlier in the pipeline. That is the, if you can achieve this, what you can achieve this, compute the branch address earlier in the pipeline, then you can overcome or mitigate this problem called as branch penalty. See here, you can see instruction 1, instruction 2, instruction 3, instruction k and instruction k plus 1. Here, instruction 1 till instruction 3 or further, they are stored in successive memory locations. While instruction 2 is a branch instruction. Instruction 2 is a branch instruction whose target instruction is IK. Whose target instruction is IK. And how many stages are there? Fetch and execute. So fetch 1, execute 1, fetch 2, execute 2, like that further. So this is a two-stage pipeline example. This is a two-stage pipeline example. Here, as we said earlier, I2 is a branch instructions. I1 till I3 they are stored in successive memory locations. IK is the target instruction for the branch instruction. Let us focus on clock cycle 3. At clock cycle 3, what is happening? At clock cycle 3, fetch of instruction 3 is happening. Fetch of instruction 3 is happening, as well as decoding and target address computation also is happening. Decoding and target address computation is also happening. While in clock cycle 4, CPU will be discarding I3 because it will not be the latest content, and it will fetch IK instead. It will fetch IK instead. So here, because of this, E is stalled. Okay, and E is stalled is for one clock cycle. E is stalled for one clock cycle. Now let us look at one more example wherein you have a four-stage pipeline. You have every instruction has four stages: fetch, decode, execute, and write. Now, if you look at the branch instruction, I2 is the branch instruction. So the branch address is computed. When the branch address is computed, it is computed at E2. While I3 and I4 are discarded because IK needs to fetch. IK needs to fetch. And when IK is fetched at clock cycle 5. So total clock cycle loss is 2. So the branch penalty is 2. Now we need to reduce this branch penalty. We need to reduce this branch penalty. And what is the technique for reducing the branch penalty? The technique for reducing the branch penalty is compute the branch address earlier. Okay, so a dedicated hardware can do this at D2 stage, and the clock cycle is reduced to 1, and the penalty is reduced to 1 rather. Now there is a technique called as prefetching. So, what is the purpose of prefetching is the purpose of prefetching is to again avoid pipeline stalls or to mitigate pipeline stalls or delays. So, here what will be happening? The CPU will be fetching instructions even before they are needed, and it will be putting them in a queue. Okay, so you can look at here. This is the instruction queue. The instructions are fetched, and they are fetched even before they are needed. The dispatch unit will be taking those instructions from the front of the queue to the execution unit. So the dispatch unit role also is to do decoding. So what is the role play of instruction queue and prefetching here? They are together resolving or mitigating the problem of pipeline stall. Problem of pipeline stall. Now let us look at this diagram. Okay, here we have clock cycle, and we also have queue length. So let us focus where the stall has come. Now stall has come at instruction 1 itself because even is delayed. Okay, now at this stage the queue length rises to 3 in cycle 6. The queue length rises to 3 in cycle 6. If you look at here, I5 is a branch instruction and its target instruction is IK. So naturally I6 is discarded. So when I6 is discarded, what will happen is actual resultant should be a stall, but instead of that, I4 is dispatched from the queue. I4 is dispatched from the queue to the decoding stage. And here again, the queue length drops to 1 at cycle 8. The queue length drops to 1 at cycle 8. Now let us look at the sequence of instruction completions. First, which instruction is completed? The I1. After that, I2. After that, I3. After that, I4. After that, IK. So this is the sequence of instruction completions. So here, even though branch instruction is there, it is not affecting or increasing the overall execution time. Why? because the branch instruction is parallelly concurrently being executed with other instructions. This technique is called as branch folding. So what branch folding has achieved? Branch folding has mitigated or overcome the impact of branch instructions on performance. So we'll stop here and we'll continue this discussion in the next lecture.